Mr. Chairman. Today I wanted to talk to you about this flying sensor node. The idea is, it's called the Atalanta project, after the butterfly. And the idea is to have a flying sensor, which you can position basically anywhere. You could fly around the space. It has to be within 10 centimeters, be capable of hovering flight. And we would also like to do some ad hoc networking and indoor usage. It is very ambitious. It was planned to be very ambitious. It's mainly supported also by a couple of companies who are interested primarily in the spin-off. So it's a sort of a visionary project. And I wanted to show you some of the problems and inspirations we found. There's a lot of applications for it. You could do 3D measurements, but of course everybody immediately thinks about military surveillance. But there are many other options of things like measurement in dangerous or hard to reach places, or 3D mapping of spaces. So animals have been flying for a long time, so how have they been doing it? Both insects and birds are at that size, about 10 centimeters. So what are they doing? So this whole project, actually, if you want to achieve it, you have to cover a lot of different aspects. Anything from the aerodynamics, wings, etc., power, to sensors and control, navigation, and finally payload. Now, I'm not going to talk about everything. We are looking at most of this first part, and I'm going to start with the flying bit, so seeing if we can get this platform off the ground. Well, if we're looking at the aerodynamics, which is the main issue when we try to create lift, we see that at this scale aerodynamics is extremely complicated, especially if you want to do it with flapping wing flight. This is a beetle, and it is flying in a wind tunnel with some smoke to visualize the flow. And as you can see, there's a lot of, well, I shouldn't say turbulence, but vorticity going on in the flow. And there's complicated things like leading edge vortices, things like wake capture and rotational circulation going on. And they all contribute to lift, but they also introduce drag. These aerodynamics are, of course, dictated by the wing kinematics, so how do the wings move? But reversed, it's also that the kinematics of the wing is caused by the pressure of the air, of course, so there's an interaction there. It is so complicated that at the moment it's not possible to do optimization for the full 3D flapping wing simulation with solid fluid interaction. One flap 3D takes about in the order of 2.5–3 weeks to calculate at the moment, so no optimization there. So we just want to copy the kinematics of insects and birds of this size, as we think they probably know what they're doing. So how do insects fly? We're mostly looking at insects. Birds are a bit different, of course. And insects, actually, they fly using their thorax. So we have the middle part of that insect. There's a head there, and of course there's an abdomen afterwards, but there's a thorax in the middle, and it consists of many different structures. And in cross-section, it looks a bit like this. It's a box. It's a stiff box. There's muscles attached to it, and it is brought into resonance, a mechanical resonance. The wings are not directly attached, at least not in most species, to the wing, but it is through a couple of joints connected to the resonating box to create a rotational motion and a large amplitude. Now, the advantage of this is, of course, that you get a direct and indirect wing drive, and you have resonant properties, and that has some advantages because you do not have any inertial losses when you're driving, accelerating and slowing down the wing. So this is actually a pretty good idea. It does mean that your wing flapping frequency is set. It is determined by the mechanics of the body. What we can build on this, so the basic mechanics, of course, is a sort of a spring with a wing on it, and that is very efficient. We have some amplitude amplification. We can have Q factors. In simple subfabrication, you get Q factors in the order of 20 in vacuum, and in air it's 2 to 3 because of the lift we're producing is causing a lot of drag and damping to the system. So we're using a sort of a ring structure. We see a cross section here with a couple of struts, and if you bring that ring into resonance, it starts flapping its wings. That's the idea, and the whole thing is compliant, so it's a structure without separate hinges. Now this is creating the flapping motion, but flapping motion is not enough. We also want the wing shape as it is flapping. This is a hawk moth, which is about 10 centimeters in wingspan, and as you can see, the leading edge is rather stiff, but the rest of it is folding back and forth in a certain way. And it has this sort of motion with lift production in the direction of the arrow. So we want that sort of motion in, if possible, a passive way. An insect does not actively rotate its wings normally. It does do some things for maneuvering, but not for normal flight. And if you can do it passively, it doesn't add any weight. We don't need actuators, etc. for this. So we'd like to do that passively as well, which we can do. So by doing some separate design of the stiffnesses of a flexible hinge, the weight distribution and stiffening of a membrane, we can do sort of the mimic that the deformation, the kinematics of that wing. I'm sorry about the flickering. It was recorded using a strobe light, so it's a bit out of phase here and there. Okay, so what do we get? This is the overall flapping device. It's flapping at 30 Hertz, which is optimal for that length of wing. So that is determined by the size of the device. We see the ring, we see an actuator. This is just a large solenoid to drive the testing. And we see the wing. Well, it's going too fast to see, so if you slow it down, you can see that this motion is created if you just bring the ring into resonance. And it starts flapping its wings and produce lift. You can also see that this wing, for example, was a sort of a Monday morning product, and it's not quite doing the same thing. So it's very critical in the mechanical design of this device. Now, that was the mechanics. We're here at the sensors. So we're also interested in, of course, the sensors, but also the steering and the control. Insects, how are they doing it? Well, they use about 5 sensors for flight control. At least these are the main ones. The Halters, hairs, eyes, and ocelli. I'm going through these. Most of these gyroscope type actuate or sensors, and the hair sensors I'm showing later. I mean that they have all been introduced this morning also by the plenary session from Khalil Najafi. So I won't go into it too much, but they have this sort of halter, this stick that is flapping with the wings, and as it is at an angle, they can use it to detect rotation of the body as a vibrational gyroscope. And of course we can introduce gyroscopes as well. Simple hairs are also used, especially for correction in gusty environments, so if there's wind gusts. So if you have a fly zooming around and there's wind, it will automatically turn into it. There's no brain action involved. it does this automatically. And if you shave a fly, and they've done this, they have a lot more trouble to stay stable in turbulent areas. Then there are the ocelli, which is a sort of 3 sensitive cells, light sensitive cells at the top of the head. And they are very primitive eyes. They don't have an image, but they do look at sort of a light distribution. And they basically say, okay, that's the lightest part, that must be up. So if you have 3 looking sideways, if this one goes up and it sees more sky, that must be lighter. So if they have the same sort of illumination, then it is level. So it's a very primitive system, but it is very fast and it works at very low light levels. So that way an insect knows which way is up. And it's very simple, but it's also simple to replicate. Now the eyes, the compound eyes of an insect are also very interesting. They are for building up an image, so they are looking for things like this. So they see flowers and mates and food, but they also use it for motion information. The problem with these is that they are not quite as quick as the ocelli, and they need a lot more light. But we have similar things which we can use, like the cameras. I want to show you one sort of idea we have on how to use this concept. Because if an insect looks at something, there is an image of that in, say, one of the compound parts of that eye, the facets. And if this moves, it has this image going through its eye, and that information is captured. So they do sort of a mapping between these things. So they have a direction and a speed information without looking at the object. Now we can do this. They can use this for seeing that they're flying forward. They see motion to the side. They see going up and down. They can see if they are rotating just by the image information. And of course they can also see if they're closer to the ground, then that seems to be moving faster than things far away in the sky, or if something is moving closer. So this gives us the option of, I'll skip this, doing the same thing with a sort of a mouse camera. Mouse cameras give you a voltage proportional to a movement vector in an XY direction. So by placing a couple of cameras surrounding this to get some images in all directions, you can actually do lots of analysis. I have to close up here, but we have cameras in certain directions. We can tune the flapping angle to produce more or less lift, and we can change something in the wings, anything to reduce it. And then if we start doing some math by combining different signals out of these cameras, we can directly drive these actuators. And it also has emergent behavior. Now if we can do this, we can do roll stabilization, we can do height stabilization, and we automatically get object avoidance. It's a fairly simple analog control system inspired by an insect, and with that I want to close off. There's a lot of things we can be inspired by, not just structures or sensors, but also things like control and the physics behind it. Okay, for that I want to thank you for your attention.